This 35th lecture, we talk more about probability distribution functions and probability density functions. In the 33rd lecture, we had introduced the concept of continuous probability, capital P of x, and the probability density function, small p of x, and we defined the mean values like this. If there is a random process to which a random variable capital X belongs, there is a random process, well, let's call it an ensemble, that is the probability of each sample is known, then if capital X be a random variable which takes on values small x lying between minus infinity to plus infinity, and if capital P of x be its probability distribution function and small p of x its probability density function, then we defined the mean value of any function of x as minus infinity to infinity f of x small p of x dx. This is the mean value, and we took various examples. For example, if f of x is x, then the mean value is simply x bar. This is not time average, but this is an ensemble average. This average is ensemble average. If f of x is simply equal to x, then the mean value is x bar, ensemble average. If f of x is x squared, then x squared bar is the mean squared value, which is to be distinguished from mean value squared. This is not necessarily equal to x bar squared. We also showed that if we take the central moments, that is, if we take x minus x bar, if we take the reference as x bar and take the square of this and consider this as f of x, then what we get is sigma squared, which goes by the name of variance, and the relationship between sigma squared and x square bar and x bar square is x square bar minus x bar squared. Is that correct, or is it the other way around? Correct. And sigma, you know, is called the standard deviation, not sigma squared. Sigma squared is called the variance and sigma is the standard deviation. Obviously, none of these makes sense unless the RP is an ensemble. That is, if the probability density function or the probability distribution function is not known, then it is simply a random process. It is not an ensemble. The mean and averages, they all make sense only if the RP is an ensemble. As an example of this, let's consider a probability density function which is uniform. We considered a number of probability density functions last time, the Gaussian, the Rayleigh distribution, what else? Exponential, and the uniform. The uniform was something like this. This is probability density function, so it's a plot of small p of x, distinguished between small p and capital P versus x. Let's say this value is capital A, this is B, and this is A. That is, the probability density function is a rectangle of height A in the range B to A. Can we say anything about the relationship between capital A, small b and small a? Why? Because minus infinity to infinity, small p of x dx is equal to 1. All right. And therefore the area, therefore capital A must be equal to 1 by b minus a. All right. And p of x obviously is equal to a. If we write this clearly, then a between x and x lying between a and b, and otherwise it is 0 otherwise, alright. And therefore, if I take x bar, that is the ensemble average, that would be integral a dx, a x dx from a to b, which would be a times a by 2 times b squared minus s squared. Is that okay? What is that? Oh, capital A is 1 by b minus a, so it is b plus a divided by 2, which is the same as a plus b by 2, okay. So what kind of operation is this? A plus b equal to b plus a. What? Commutative operation, alright, b plus a by 2. And x squared bar, you can very easily show a x squared dx between a and b, and therefore this is capital A by 3 b cubed minus a cubed, which I can write as b squared plus ab plus a squared divided by 3, alright. And therefore the standard deviation, no, the variance, which is equal to x squared bar minus x bar squared, is equal to b squared plus ab plus s squared divided by 3 whole squared, no whole squared, minus b plus a divided by 2 whole squared. That is equal to b squared plus ab plus s squared divided by 9 minus b squared plus twice ab this is 3, thank you, b squared plus 2ab plus s squared divided by 4, and you can now simplify this 12, so 4b squared plus 4ab plus 4s squared minus 3b squared minus 6ab minus 3s squared. The result is what?
A minus b whole squared.
A minus b whole squared or b minus a whole squared? Okay, b minus a, we usually write the larger quantity first, although it's a squared, divided by 12. In other words, sigma is equal to, now you cannot say a minus b or b minus a, it is unique, b minus a divided by square root of 12. This is the standard deviation. This is a result, although derived very simply, this is a result that will be very useful in the courses on communication theory, also in digital signal processing, because in many applications it is convenient to assume that the probability density function is uniform. It is convenient. It is far from reality, but nevertheless it gives you an idea as to how things go. For example, in digital signal processing or in digital communication, when you will talk of quantization, you will be required to find out the standard deviation sigma or the variance of the quantization noise, and uniform distribution will come out very handy, although it is not strictly a uniform distribution. No process in reality is a process with a probability density function which is uniform over a range. The most popular probability density function, in contrast to uniform, the most popular is the Gaussian. Popular because many of the physical phenomena can be modeled quite accurately by a Gaussian model, and as pointed out last time, the Gaussian model is, Gaussian probability density function is square root of 2 pi sigma e to the power minus x bar squared divided by 2 sigma squared, and the range of the variable is minus infinity to plus infinity. This is the Gaussian probability density function, and I have told you the reason for these constants 1 by square root 2 pi and sigma squared is of course the variance, x bar is the ensemble average, and these occur because integral px minus infinity to plus infinity has to be equal to 1. This is the constraint for which this constant is 1 by square root 2 pi times sigma. If you plot this versus x, then obviously the maximum shall occur when x is equal to x bar, and therefore it is a bell shaped curve like this, goes to 0 at minus infinity or plus infinity, but the peak occurs at x bar. Unfortunately, the corresponding probability distribution function, that is capital P of x, which is integral small px dx, can you tell me the limits? Minus infinity to small x, alright. Unfortunately, there exists no closed form for this. The only thing that one can do is the following, that the maximum slope would be at x bar, alright. So it is like this, where this point somewhere here is x bar. This is the probability, this is the distribution of capital P of x versus x. All that one can do is compute this numerically. You can compute small p of x, and the integral you can compute by a small computer program. No analytical formulation exists. However, this is no disadvantage. The advantages of a Gaussian probability density function are many, and the features which characterize this, which make this density function the most popular density function, are first of all that many physical processes can be modeled by a Gaussian process, approximation to physical processes. Number 2, well, obviously it's a simple analytical function, easy to handle analytically, although as I have pointed out, it cannot be integrated to give a probability distribution function. No analytical form, no closed form exists. This is easy to handle analytically. If you have two random variables, okay, then the joint probability density function is also Gaussian, alright. If there are two random variables x and y, whose probability density functions are known, then the joint probability density function, which we shall define a little later, the joint probability density function is also Gaussian. In fact, Pxy, a joint probability density function, is simply 1 over 2 pi sigma x sigma y, alright, e to the power minus x bar squared divided by 2 sigma x squared plus y minus y bar squared divided by 2 sigma y squared, which is also Gaussian, alright. This is not true for other distributions, for other density functions, for example Rayleigh function, it is not true, alright. Gaussian probability density function enjoys this peculiar and simplifying feature, that the joint probability density function is also Gaussian. Now there is a condition attached to this, that is the two random variables x and y must be statistically independent of each other, x and y statistically independent of each other. Even if this is true, other distribution functions or other density functions do not enjoy this privilege, that is a combination of them does not give the same kind of distribution or density. That is the third. The fourth is that this combination is not necessarily limited to 2 random variables. It can be expanded to include any arbitrary number of random variables, alright, and it is very easy to see why it is so, because it is simply, if they are statistically independent, then the joint probability density function, which we are going to define in a moment, would be Pxx times Pyy times Pz and so on, and therefore it can be extended to an arbitrary number of variables, arbitrary number of random variables. And the fifth and perhaps the most important is that a Gaussian random process, a GRP, can be described, well, when I mean RP, I mean the ensemble, okay, otherwise mean and variance and other things do not mean much. A Gaussian random process or a Gaussian random variable can be described completely by only its first and second moments. In other words, x bar and x squared bar, these are adequate to describe a Gaussian random variable. This is also obvious in the distribution, in the density function. You see, all that appears in the density function, all that appears is x bar and sigma, and this is adequate to describe the complete random process, which is of course an ensemble. This is a very distinct advantage, and this is not true for other density functions. So in practice, whenever we want to complicate our life a little bit, then we assume that the distribution is Gaussian. If we do not wish to complicate at all, then we assume that the density function is uniform, alright, and we will do this as per convenience in digital communication and also in digital signal processing. I don't know, if you study a course on digital control, perhaps you will get the same type of advantage and same type of assumptions. Now we consider this question of joint probability. That is, first we consider 2 random variables, 2 RVs. You recall that in the discrete case, discrete probability case, we had said the joint probability of 2 events A and B is given by the Bayes theorem, which states that it is the conditional probability of A given that B has occurred multiplied by the marginal probability of B, or in other words is the same B given that A has occurred multiplied by marginal probability of A. Now how do we do such things in the case of a continuous variable? In the continuous variable, you remember that P of x is not a ratio of probabilities, ratio of discrete probabilities, but it is the probability that the random variable x assumes a value less than or equal to small x, alright, and therefore how do I define the probability of 2 random variables, that is joint probability of 2 random variables. Now these 2 random variables may come from the same process or may come from different processes, alright, it does not matter which way it originates, it matters later when you talk of statistical independence, but for the present let us say that there are 2 variables, capital X and capital Y, alright, and we are interested in the joint probability distribution function. That is, we are interested in a Pxy, then this is defined as the probability in the same way that capital X less than equal to X and in addition capital Y less than equal to Y. This is the definition of joint probability in the case of a continuous variable. In the case of 2 continuous random variables, capital X and capital Y, which interact with each other, that is, we are interested in an event in which both the random variable capital X and capital Y are important, and this is the definition. Obviously, according to this definition, that is capital Pxy equal to the probability that capital X less than equal to X, capital Y less than equal to Y, several properties immediately follow. Number 1, that it cannot be negative, probability cannot be negative, and the probability upper limit shall be 1, that is when both capital X reaches its limit and capital Y reaches its limit, then the probability is 1, and therefore 0 less than equal to P x y less than equal to 1. This is the first property. Second, where we of course assume that in general both x and y can vary between minus infinity and plus infinity, alright. It is important to make this assumption for the rest of the properties. We can of course say if the range is finite, let us say some minus a to plus b, then all the properties that I am going to state, minus infinity shall be replaced by minus a and plus infinity shall be replaced by plus b. This should be obvious in the context. Now second property is, if I take p minus infinity y, that is capital X less than equal to minus infinity, obviously the probability is 0, and this should also be equal to p x minus infinity and equal to p of minus infinity minus infinity. Agree? Any of them becoming minus infinity, that is the lower end, well, it means that the probability is 0. 3, probability of infinity and infinity, obviously this is equal to 1, okay. Fourth, dp xy, well, since there are two variables, I have to differentiate, I have to make partial differentiation, and therefore this d now becomes the crooked delta x, and also dp xy partial differentiation with respect to y, both must be, what can you say about their values? Can they be negative? No, because capital P x y is a non-decreasing function of x as well as y, and therefore they must be greater than equal to 0. Can you put a limit on their upper limit? No, they could go as high as infinity. Can they?
Yes, sir.
They can. All right. Fifth, if I take p infinity and y, this is p y y. We use a subscript y to denote that capital X has taken all possible values, alright. That is, we are considering the probability of small y only, irrespective of what the value of capital X is, alright, that it can take any value less than equal to infinity, and in the sense, in the same sense as in the discrete case, we can call this the marginal probability distribution function of the random variable capital Y, the marginal, and this is why we use a small y. Similarly, p of x infinity, we shall use p x of x. Now it is important to notice that this is not necessarily equal to p of y. That is, if both events are occurring and we are only concentrating on y, alright, it is not necessarily equal to py. The marginal probability there in the two cases, discrete and continuous, are distinguishable by this, because if the event is related to x, that is, we are considering a joint event, joint probability density function, then this p, the functional form, is not necessarily the same as py. The functional form could be different. It is true only in the case of Gaussian random variables that the functional forms are the same, alright, not otherwise. Similarly, px of x is not necessarily equal to px, not necessarily, I say. For some distributions, yes, but not for all distributions. Now, in similarity with the probability density function for a single variable, we can now define a joint probability density function. Joint probability distribution function is pxy. Joint probability density function Well, I will call this JPDF, all capitals, joint probability density function, then small j, small p, small d, small f. To avoid any ambiguity, this is the joint probability density function. The d, small d, now stands for density, and we shall denote it by pxy. Obviously, what we have to do is to differentiate partially with respect to both x and y, and therefore it is the second partial of capital Pxy with respect to x as well as y. Does it matter which differentiation we do first? No, it should not matter. So it is the same as d2p xy dy dx. What is the physical significance? The physical significance of the joint probability density function. If you recall, the physical significance of a single variable probability density function was that px dx was the probability that capital X lies between small x and x plus dx. In similarity with this, we can now make a physical interpretation of small p xy, and this is precisely p xy dx dy is the probability, joint probability, that capital X lies between x and dx, and in addition capital Y lies between small y and small y plus d small y. This is the physical interpretation. With this physical interpretation and the definition that small p xy is the second partial of the probability distribution function, that is dx dy, with this several properties of the function small p xy jpdf follows. For example, property 1, small p xy obviously is greater than or equal to 0. We cannot put an upper limit on this, but it must be positive. It must be non-zero, minus infinity, less than x, y, less than infinity. Property 2, if we integrate from minus infinity to plus infinity, small p xy, now we have to specify the variable. If we integrate with respect to both the variables, then we have to use a double integral. Obviously, this is equal to 1. All right. 3, capital P xy in terms of small p xy obviously is minus infinity to x, minus infinity to y, small p xy dx dy. The fourth property, pardon me? What is d by dx?
It's not dx, dy should be dy dx. Yes, sir.
Okay. Provided x and y are related, if they are statistically independent of each other, then it does not matter.
So
is this point clear?
It can be related. So we will write dy dx.
Right, that is the most correct one. This interpretation, this writing would be correct if x and y are independent of each other statistically. Is the point clear? Alright, so we must write dy dx because y is the inner integral. This is true, but if I write the other way around, that will be true only for the specific case that x and y are statistically independent of each other. Then we can separate this out. Alright, very good. Now if I integrate with respect to, let us say, y only, pxy dy, it means that we are considering the marginal probability density function of the variable x. So pxx is the marginal probability density function of the variable small x. It is not necessarily equal to small p of x. The functional form can be different. Similarly, PYY, the marginal probability density function of the variable y, too many definitions, you must not get lost in the terms. Each term must mean, pardon me, minus infinity to x, pxy dx. Is it okay? I made a mistake. This should be minus infinity to plus infinity, and this should also be plus infinity. Otherwise, the integral will be a function of y or x. We want to get rid of y, so we must integrate from minus infinity to plus infinity. Similarly, for PYY. And in general, if we integrate from x1 to x2 and from y1 to y2, small p xy, what is the order? dy dx. What is the physical interpretation of this? This is the probability that capital X lies between x2 and x1, and in addition capital Y lies between y2 and y1. I should have said the lower limit first. Capital Y lies between y1 and y2. This is the physical interpretation. Obviously, if you want to represent this distribution function, the joint probability distribution function Pxy or small pxy in the form of a graph, you need a three-dimensional plot, and three-dimensional plot is not easy to show on 2 dimensions. All right. Now, what will this represent? It will represent a surface. Okay, x and y are on this plane, z, that is the value of small p or capital P, is vertical, and if we plot at all points x and y over the possible range, then what we shall get is a surface, and therefore we shall not attempt that because it is difficult. Now, the joint probability density function is used in the same manner as the probability density function of a single variable to determine the ensemble averages. That is, if we have a function of x and y, 2 variables, then the ensemble average or the statistical average of this function is defined by a double integral from minus infinity to plus infinity, minus infinity to plus infinity, f of xy, pxy, the joint probability density function. Then now the order is not important, dx dy. All right, we can integrate with respect to anything because the limits are the same. This is the definition of the average of a joint process of 2 random variables. All right. For example, if f of xy is simply the product of the 2 random variables xy, then xy bar is equal to minus infinity to infinity, minus infinity to infinity, xy pxy dx dy. To make things more concrete, let us assume a particular form of this density function. Let us say the density function is uniform. This is the most simple assumption that one can make. Let us assume that pxy is uniform and the range is finite. That is, let us say this is 1 by x2 minus x1 times y2 minus y1. That is, within the range x2 minus x1 and within the range y2 minus y1, the probability distribution function is a constant. Now, if that is so, then by substituting,
will it be P or capital?
pardon me?
Will it be capital PXY?
No, it is small pxy, density function. In the previous case also, it was a probability density function which was considered to be uniform. If that is so, then the integral, it is very easy to show what the integral is, minus infinity to plus infinity, x y divided by x2 minus x1 y2 minus y1 dx dy, and this is obviously equal to x1 plus x2 by 2 multiplied by y1 plus y2 by 2.
Integration limits are no longer minus infinity to infinity.
There will be x1 to x1.
That is correct. So what should be the first integral?
y1 to y1.
Okay, and this should be x1 to x2. Quite so. Now we shall show that this is nothing but the product of the two averages. Alright, it is the product of x bar and y bar. It is the same as xy bar. The reason, before I prove this, the reason is that whenever a probability density function is like this, is uniform, and the involvement is simply the difference between the two limits, then it is as if the probability density function Pxy is the product of marginal probability density functions, because 1 by x2 minus x1 is independent of y, 1 by y2 minus y1 is independent of y. In other words, Pxy, if this is a product of Pxx and Pyy, which would be the case if the two marginal density functions are Gaussian, for example. In the uniform case also, this is true, and these two these two random variables are therefore statistically independent. This is necessary as well as sufficient condition for statistical independence of x and y. When we are considering statistically independent, when we are considering the joint probability density function, the necessary and sufficient condition for the two random variables being independent of each other, statistically independent of each other, is that Pxy is Pxs multiplied by Pyy. And you see in this case that x1 to x2, y1 to y2, Pxy, xy dy or dx, dx, if the two random variables are statistically independent of each other, then I can write this as x1 x2 Pxx x dx multiplied by y1 to y2 Pyy y dy, and this is obviously x bar times y bar. The averages are to be taken with marginal probability density functions, and this is true for this particular case of two random variables. And as I said, if the density functions are statistically, the density functions are Gaussian, then also this is true. With this introduction of continuous probability, discrete probability, and the definition of the averages, we now make a summary of what we have done and introduce some new terms. And these terms come in the context of, one should be careful, I will go very slow, in the context of random processes. That is, we are now making further classification of random processes. All right, further classification of random process. One of the classifications that we have done already is that the random process could be discrete or continuous. In the discrete case, the random variables assume only certain specified values, specified levels of values, and the probability distribution function is, what is the shape? It's a discontinuous, a staircase type, because it must be a non-decreasing function. No, is that correct? Can it be a decreasing function?
Yes, sir.
It can. In the discrete probability case, there is no restriction like this. However, there is a restriction on the probability density functions. They must all be delta functions. Isn't that right? If it is a staircase could go up, could go down also, alright? Staircase is not necessarily going up. But it is true that whether it goes up or down, the density functions, PDFs, are delta functions. They contain only delta functions, nothing else, alright? On the other hand, in continuous case, the probability density function is a continuous function of the random variable, the possible values of the random variable. Alright, it is a continuous function. This basis of classification we have already done. Now, yeah.
Sir, how can probability distribution function, I mean, be a downward staircase? That would imply that the PDFs are negative deltas. Wouldn't that?
Yeah, we are talking of the discrete
Yeah,
level.
but how can we have a negative delta?
Okay, we cannot. Alright? We cannot have a negative delta.
In negative.
So the class divided on this issue, probability density function for a discrete random process, can we have a negative delta? Can we have negative deltas? The probabilities in the discrete probability, as the value is increasing, does the probability have to increase? Not necessarily. And therefore we can have negative deltas. Why not? Anurag, what is your objection?
So that would mean that probability density is negative.
Yes? No, not necessarily. It is a probability density.
Decrease in density.
You can't say positive or negative because probability density is a combination of delta functions. And you cannot say it is positive or it is negative. It's a combination. It's a combination. Density function negative does not mean that the probability is negative. Probability cannot be negative. Probability distribution function has to be positive. Is that right? It has to be lie between 0 and 1. But the density, which is a differential coefficient, obviously can be negative. In the discrete event case, there is no restriction. But in the continuous event case, because of the definition, because P of capital X, P of small x is a probability that capital X less than equal to X, it must be an increasing function or a non-decreasing function of small x.
How do we define a discrete?
PDF. How do we define PDF in discrete case?
Oh, we just plot it. Okay? Capital P of X, X assumes some values. Let's say these are the values, X1, X2, X3, X4. So we make X1 as this, X2 as this, maybe X3 is this, and X4 maybe this. Then if you want to put it in the form of a function, it's a staircase function. Well, if you want to put it as a function, otherwise you consider this is discrete.
So that would imply that the probability that X is somewhere between
No.
X1 and X2, that's finite.
No, there is no probability, that's zero. If you want to view it as a staircase, it's up to you.
So why do we define a small px?
Small px cannot be defined. That is the question. If you want to define a probability distribution function like this, then the probability density function will mean something. And as in the example that we have taken a staircase like this. We have taken an increasing staircase, and therefore the probability density function in the discrete random variable case was a conglomeration of delta functions. Alright, it depends on how you define.
So, but how is it actually? Suppose we have x between x1 and x2.
Yeah, the probability is 0.
0. So, but you assume it to be the same.
It is 0? Oh no, okay.
So you can't have a steady
Why do we need all this
And
in
therefore-
case of discrete?
It has to be
And
only.
therefore in the discrete case,
There is no question of a PDF, small PDF.
there is no question. If at all you define,
Then we have to define probability distribution.
okay, then you have to define probability distribution function like.
So we could
Other
even
than
This is not probability distribution.
This is not probability distribution. Okay,
So instead we could put the green lines across the x-axis.
let's not do it at all. All right.
we would have a linear interpolation.
All right. What he says is, Concord says is, let's have the green lines here. Well, even then,
So
the delta
but
function.
then we know that in discrete we cannot have a value between x1 and x2.
That's why it is 0.
So it does not exist. There is no question of being
Okay. Therefore, the green line is also not permitted.
No, but
It doesn't exist between those lines.
when we can say its probability is 0.
No, not that. It's not possible.
It's an impossible event.
Hence
Its probability is 0. What is wrong with that? All right. To cut down this controversy, we do away with the definition of PDF. In the case of a discrete random variable case, I had to bring this in because by mistake I have shown you a picture of probability distribution function for a discrete random variable as an increasing staircase, and I have said that the small pdf is a series of delta functions. It doesn't mean anything in the case of a discrete random variable. Alright? The second basis of classification is something artificial. An RP, a random process, you know, it's a collection of random time functions, isn't that right? And the definition was for a random variable that its future value cannot be predicted. Alright? So, a random process basically is non-deterministic. I must have your complete attention now, because we are going to make an artificial definition of deterministic random process. Well, obviously in the context of discussions held so far, this term should have no meaning, but you will find in electrical engineering, also in other branches of science and engineering, that they take help of in situations it is convenient to consider a certain process as random, but of the type of deterministic type. Let me give you one small example. Suppose you have a collection of time functions which are of this form: a cosine omega t plus theta, and where it is not a it is not the amplitude which is a random variable, but it is theta which is a random variable. That is, you take an ensemble, let's say 100 such time functions. Theta for each sample is a constant. Theta for each sample is a constant. You take x1, x2 up to, let's say, x100. For each xi, theta I is a constant, and therefore the randomness is not over time, and the future value of xit can be predicted. Is the point clear? No. I said that a random process, when you defined it, I said it's a collection of random time functions. Now, in certain physical situations, it is convenient to consider not random time functions, but randomness over something else. For example, phase. You see, if this is considered as a random process, if theta is random, let's say it varies between 0 and 2 pi, with maybe uniform probability or whatever, maybe Gaussian probability, I don't care. It is not the amplitude. If the amplitude was random, then it would have been a random time function, and its future value could not have been predicted. But amplitude is not random. What is random is theta. and this randomness is not over time, it's over an ensemble. I have 100 such processes, 100 such frames, all right, and in each x of t, x1, x2, x100 have been plotted. Theta is a constant for an individual member of the family, but it varies from 0 to 2 pi, over 0 to 2 pi, over the ensemble, all right. Then obviously this is not a random process over time, it is not a collection of random, how should I say it? It is a collection of random time functions.
But not definite, but they are arbitrary but definite.
As a family, they are random, but as a sample, it is deterministic. That is, theta for the ith sample is theta I, and therefore x of t can be predicted at any value of time. The randomness is not over time, but it over the ensemble, over theta, and therefore this process is called a deterministic random process. And you shall come across this umpteen number of times in your communication course. That it is a deterministic process, but there is one particular parameter which is random. This is not the amplitude, but it is the phase here. If the phase is random, then it is a deterministic random process. It is somewhat an artificial definition, but it helps in analyzing the situation. It helps in using all the concepts that we have generated so far in the context of random processes to be applied here to theta, all right, and therefore this process is called deterministic random process. In future, when somebody mentions that this is also a random process, you should not be surprised, all right. Such processes, this is a kind of an artificial definition, but it helps in analyzing, and therefore engineers live with this. We'll close it here.